Can we dim the lights?
Yes, I can.
All right. So yeah, this is part two. And today I'm going to explore some of the limits of the strong interaction force QCD with nuclear PDFs, look at how we get some of that information, where we need some information, and what the EIC might be able to discover for us. So in terms of discovery, I think it's useful to look back over history a little bit. And I like this quote by Isaac Asimov. The most exciting phrase I hear in science is not the one that heralds new discoveries. It's not eureka, that is, I found it, but instead, that's funny. And so there are many serendipitous scientific discoveries across time. You know, penicillin, Alexander Fleming, he left his lunch out for a week and it grew. X-rays, microwave oven, rubber, Post-it notes, cosmic microwave background. Penzias and Wilson were working with radio noise. They got radio noise in their antenna, and they were trying to figure out what was wrong. As the electronics broken, they're in New Jersey, near New York. Are they getting distractions from stuff going on in New York City? Turns out there were pigeons living in their microwave horns, so they removed the dielectric that the pigeons left, and none of it went away. And sure enough, they discovered cosmic microwave background, and that was good for a Nobel Prize. So scientific progress is not always a direct path, but it is about recognizing unexpected patterns at the fringes of your expectations. So you need to be prepared for these. And so also want to remind you that ours is an experimental science. And this is one of the cartoons I have tacked up on my wall. And it says, the caption is, how many of you think that Volkswagen will clear the athletic field entirely and hit the abandoned warehouse? Thanks to the innovative labs of teacher Herb Crenley, physics quickly became Westphal High's most popular course. And I like the cartoon, but in particular, if you look on the chalkboard, those are real equations. So apparently the cartoonist actually took a physics course and remembered the equations enough to get the equations on there. So, okay, we may be influencing future physicists, but we're also influencing future cartoonists. The other one is this is an article I like that is taken from the Fermilab News back at the beginning of Run 2, when they were getting ready to run the Run 2 data at the Tevatron. And the title is Data Make You Smarter. And basically the premise is that you can do lots of preparatory stuff, but when you actually have the data and sort through it and looking through it, you get very creative and you're very motivated to find things. And so if a little bit of data, the Tevatron make you a little bit smarter. At the EIC, we're going to have a lot of data, and so we're going to be a lot smarter when we get there. And so this is what we're looking forward to. We're in the process now of we just shut down Rick, transitioning to the Electron-Ion collider. And so that's what we're aiming for. So in terms of the as a person that does the PDFs, I tend to think of this in terms of the QX plane. Again, Q, that's the energy you're probing the proton or nucleus with, and then the X is the corresponding momentum fraction, at least in the leading order. As you heard yesterday, there's your K and X, and there's some relations that go beyond that. But typically, when we've been doing our analyses, we've been making very hard cuts in the data. And particularly, we make a Q cut. We say we're going to forget everything at low Q because that's a non-perturbative region, and we're not very good at non-perturbative physics, and we don't want to go there. So we cut out all this data, and then we make a W cut, which is the final state mass of the final state hadronic system, and we cut that out because we can get into resonances, and at high X there are all sorts of issues, and that's illustrated here. At high X, we have problems with target mass corrections. There are important deuteron corrections that come in. At low Q, as I said, non-perturbative problems, target mass corrections, and low X, we have all sorts of very interesting things: shadowing, recombination, resummation, saturation. So historically, we've been searching, as the cartoon suggests, we've been looking under the lamppost because that's where the light is. But sometimes the interesting things are not in the most obvious places. And if we really want to understand things, if we think we really have the theory down, we want to be able to probe out here. And this is a region where, for example, JLab in particular is probing. And then the low Q region, the EIC is going to have a lot of data down here. So if we can push the perturbative, non-perturbative boundary, that'll be very interesting. And also low X, it won't go as low as Hera, but if we can do that with the heavy ions, then we pick up a factor of 8 to the 1/3, which can be important in looking at some of these processes. So that's the goal. That's where we're headed. And I've been working with the nuclear CPEC collaboration in particular. There are a number of groups, but you're going to get sort of our perspective. I'm a little bit biased there. This is the group of us back at actually the Grenoble DIS that are working on this. And over the years, we put out the NCTEC 15 set of PDFs about a decade ago, and that was wonderful. But since then, we've been doing spin-off projects and looking at different things and trying to, push those boundaries further and adding new processes. And this is just a one-slide overview, but this is what I'm going to take a look at and show you how we sort of discern all the different properties of the proton and the nuclei. So let's start with the proton. And as I said, here's the QC Lagrangian, very simple, fits in a coffee cup. And with the proton, we've been doing that for many, many years now. And the accuracy of that is remarkable. For many of the kinematic regions, we've got that uncertainty down to less than 1%. And the combination of the Tevatron and Hera and the Large Hadron Collider, along with other measurements, have that very, very well known. And so that's wonderful, but let's try to leverage that. If we think we really know what's going on with QCD, we can leverage the proton information, and instead of just doing the proton, we can do various nuclei. And that's great because you're not just measuring one hadron, but now you have 208 you could try around. Of course, when you go to the nuclear case, instead of all these complications that I illustrate here, there are all sorts of other things. You've got shadowing, jet quenching, quark-gluon plasma, fermion motion to deal with, all sorts of things. So lots more experiments you can do. But while we're expanding up in mass, let's go down in mass. And if we can do the proton, what's the simplest hadron you can come up with? Well, the pion. That's just a quark and a quark. And so let's see if we can do the whole spectrum. And then instead of just coming at this from the parton model perspective that I showed you last time, there's a new player in the game, lattice QCD. And so the machines are getting more complex, so they can do larger lattices, and that can actually do things like that can do quite a bit on the proton, especially the pion. That's a very simple case, and they're even trying to do light nuclei, which actually turns out to be quite important for us. Now, I've been mainly talking about the collinear parton distribution, but you can also talk about polarized parton distribution. So talk about spin, because that's going to be a key element of the EIC. And then you can talk about the transverse momentum distribution, parton distributions. That is, you can talk about the transverse motion of the quarks within the proton. And then you can talk about the generalized parton distributions, which talk about the spatial distribution of the quarks inside. And these are things, these are going to be the focus of going forward, what JLab is doing, and that will lead on to the EIC. So there's a whole spectrum of things we can do there. Now, let's see. So let's go from the nuclear talk about the nuclear PDFs. And first question is it just a bag of protons and neutrons? That'd be the simplest assumption. You say, okay, I take the proton, I assume isospin symmetry works, that gets me the neutron. And if I want lead, I just put a bunch of protons and neutrons in a bag and go from there. So let's try that out and see if it works. And so here it is. I think they found this stone back in Fermilab when they were digging it up. And I think this is proton data, deuteron data, and iron data. But if you go and make the ratio of iron to, say, deuteron, imagine deuteron is just a simple proton-neutron combination. We'll have that as a standard for a pure isoscalar target. You divide out the nuclear numbers, you find this ratio, and basically this is a nuclear correction factor. And this is how iron changes compared to just a simple model of a bag of protons and neutrons. And you see it's depressed a little bit, goes up a little bit, But overall, within 10%, the assumption that it's just a bag of protons and neutrons is correct. So if you're okay with 10%, you just put them in a bag and say you're done. But of course, we'd like to do better than that. We'd like to do better than that. And also, we ask the question, is this ratio independent of energy, independent of nuclear A? Does it depend on whether you're doing the F123 structure function? And all those things, if we're going to go from a 10% level to a high precision 1% level like the proton, that's going to be the challenge. So here it is, iron compared to just a bag of protons and neutrons. It's close, but we need to do better. We need to do better. So now, one of the challenges that we had is that, for example, when you take this ratio and you measure it in charge current processes, or neutral current processes or charge current processes, we seem to get different results. So up here in my cartoon, I have, for example, a lepton comes through. It probes the nucleus with a photon. And again, we saw yesterday, you're going to get a charge average of the quarks in there. Dominantly, the up quark and charm quark, which are charged 2/3, compared to the down and strange, which are charged 1/3. So you get one measurement there. And this is very easy to do. Photons, that works very well. But we can also do a charge current measurement. And so, for example, if I take a neutrino can come in and it will emit a W, and then it goes to a lepton. I can measure the outgoing lepton. And then I'm probing this not with a electromagnetic current, but a weak current. Okay. And the weak current is much weaker, but it gives me different combinations. In particular, that's a good way to get, for example, the strange distribution, as I'll show you in a moment. But if we look at the nuclear correction factor we get from the two, with the neutral current, I get the blue curve, and with the charge current, I get the red curve. And they're close, but they're not quite the same. They're not quite the same. So it looks like there's something we don't understand between these two. The universality that should be there, maybe we're missing something. And it could be a variety of things. For example, in one case, you have a photon traveling through nuclear matter, and the photon interacts with charged particles, whereas in the other case, you have a charged W traveling through nuclear matter, and maybe those are different. So maybe there's some nuclear effect we're missing. But that's key, and that's that's a sort of a long-standing problem. I call it sort of the split personality, because if you ask what is nuclear correction when you do charge current or charge lepton with a neutral current, or W charge current, you get different results. And in fact, to go a step further, let's just plot the data. So here I'm plotting the data with the charge lepton, and you see that sort of follows, kind of turns over like this. And then when I plot it with the neutrino data, it has a different characteristic, a different shape. And so the question is, what is the correct nuclear correction? Are these data sets compatible? And in fact, we've done some extensive analysis with this, and it seems to be an outstanding question. And as I said, this is important for, in particular, the strange, but it's important for flavor differentiation, because the neutrino deep inelastic scattering gives us 4 linear combinations of the quarks. So I can do, if I do a neutrino, I get this combination. I can do an antineutrino, I get a different combination. And F2 is a parity violating combination. F2 is a parity conservative combination. F3 is a parity violating combination. So this is very powerful. It gives me 4 linear combinations, where if I probe it with just a photon, then I only get 1. So this has been very important. That's a good way to get the strange. And the challenge with getting the strange otherwise is, here's a plot of what the partial distributions are. Here's the up quark, and you see roughly there are twice as many up quarks as down quarks. And then the strange quark comes just from a gluon splitting to a strange anti-quark pair. Here's the gluon I have to divide by factor 5 to make it fit on the curve. But the strange has the same charge as the down. You can distinguish the down and the up because they have different charges. That gives you a handle. But the strange quark just looks like a down quark. And so anytime you try to measure, say, a strange quark, it'll be buried underneath the down quark. So you need a process that will give you the strange quark without being masked by the down quark.
Brett, we have a question.
Yeah. Oh,
Yeah, so in the problem, the split personality problem where you are seeing different curves, you mentioned that the energy squared is 5 GeV squared. And how do you even see the charged current?
that it's a virtual. That's a virtual process. So these are, for example, NewTev is fixed target done at Fermilab on 700 tons of iron, and so they're relatively low energy, but it's a virtual W, which also means the cross section is rather low. So you're challenged because the neutrino has a very low cross section. Neutrinos go right through the Earth on average. And then this is a virtual process. So you're cheating energy conservation. You're working around 20, 30 GeV, but you're exchanging an 80 GeV boson. And so you've got to use that. You've got to use Heisenberg's uncertainty principle. And it means that's going to happen for a very short time at a very short distance, and the cross section is going to be low. So that's one of the challenges. That's why the statistics of the neutrino DIS are very difficult. So, yeah. And in a moment, I'll show you that's where the EIC can help, because that's going to have a larger energy. So how do we get at the strange? And one of the nice tricks we can use is if we do neutrino nucleon scattering, then sometimes, I'll scatter a W particle that will change a strange into a charm. And then the charm sometimes will decay about 10% of the time leptonically to kick out a muon. And so what I do is I count the number of opposite sign dimuons. And when I see that, because the charm is heavy and kicks out the muon, that will give me a signal that I had a strange quark in there. Okay. With a down quark, typically you get down to the up quark. The up quark is not as heavy. It will decay muonically, but the muon will typically be lost in the jet. And so you don't have that. And so you count the number of single muons, that gives you the number of down quarks. You count the number of dimuons, that gives you the strange quark. There's some details there. That's the theorist perspective. It's a little bit more complicated than that, as the experimenters will tell you. But roughly that ratio will give you the strange quark. And that's a very powerful way to get at the strange quark. And before the LHC, that was the best approach we had. Now, at the Large Hadron Collider, you can make many W's and Z's because you have large energy. And and you can do this in protons. So you can check here without nuclear corrections. And then LHC also did proton lead. And then you can look back and see what you get for the nuclear corrections. And so here's what they did. To make a W boson, what you can do is you can do things like you can do US and CS. Okay, so the W will linearly depend on the strange quark distribution, but the Z, that's a neutral particle, that comes from things like SS bar and CC bar. But the key element here is the W is linearly dependent on S, the Z is quadratically dependent on the S. And if I make a ratio, basically that just gives me the strange distribution. So that's how we did it. And in fact, this is one of the exercises that we're going to do with XFitter on Thursday. So we're going to try this out. And so what they found is they looked at the ratio. They looked at the ratio of S and S bar compared to D bar. And let's think for a moment what we expect for this. So the S quark is a relatively heavy quark. Maybe it weighs 500 MeV or something like that, whereas the D is relatively light. So the S and S bar, they come from gluon splitting. And because the S is heavier than the D, you would expect that the S is smaller than the D. So you would expect this ratio to be small. And in fact, this is the status of some years ago, but the early PDFs estimated this ratio to be about a half. That is, the S bar to D bar ratio is about a half. And that seemed reasonable. The S is heavy, it's harder to make. So you make more D bars than S bars, and that seemed to fit the data, at least the fixed target data. But then Atlas came along and it found this value. It found not only was it not a half, it seemed to be 120%. It seemed there were more strange quarks than down bar quarks. And that was very strange because, again, the argument is these come from gluon splitting a quark and a quark pair. If the S is heavier than the D, why should you make more S's than D's? And that's an interesting puzzle. It's one that's still an open puzzle. One important difference that doesn't show on this plot is the fixed targets are typically done in a momentum fraction of about 0.1, whereas Atlas was measuring this at about 0.01. So one possible way to reconcile this is you can say, okay, well, it's 1/2 at larger x and 0.0 and this at smaller x, but still, that allows you to sort of find a consistency between the two, but it doesn't explain sort of the fundamental question of why you expect the S bar to be less than the D, but in fact it's higher. And so again, this is a outstanding puzzle. And as I said, on Thursday we're actually gonna run this case. Yeah, question.
If we know the ratio on one scale, can't we use evolution? Were you saying that these were measured at different scales or different momentum fractions?
These are measured at a different momentum fraction.
Oh, sorry.
This is fixed target, so you're at a higher momentum fraction. And because Atlas has a much higher energy, that can probe to smaller x. Yeah, so yes, the DGLAP can get you between different Q values. These are different x values. And so you can say, okay, that saves me. I can reconcile those, but it doesn't explain intuitively. This doesn't make sense. Intuitively, you think S should always be less than D, and that just doesn't add up. And in fact, this was done originally with the proton, and then since we've checked this with proton lead, and we also see the same type of behavior. So it seems to suggest at higher x, this is low. At lower x, this can in fact exceed 1, but why that happens, no idea. So we're going to try this with XFitter, and here's the obligatory advertisement for XFitter. It's not just for protons, it can do nuclei and mesons. It can also do fragmentation functions, and it's quite universal. So we'll talk about that on Thursday. Okay, yeah. And in fact, so here, here's what we see if we look at the, strange distribution. Depending upon it, kicks up quite a bit. And again, I can make that fit very well. But if I really squeeze down, for example, if I really squeeze down on the normalization uncertainty, I can get a very low chi-squared. But then this is what my gluon looks like. And you have to be suspicious because when you start looking at things like that, you say, gee, is that really how nature goes? Or are you just sweeping your uncertainty into the gluon distribution? And that's one of the things we're always concerned about. The gluon is very uncertain. The strange quark is very uncertain. And so are we really determining it, or are we just sort of pushing uncertainty into that? And yeah, so the punchline here is the strange PDF driving the data, or is it the other way around? Are we really measuring nature or just solving a problem? So the EIC is actually going to give us a big handle on that. So again, here's the epoch detector. And what you can do with the EIC, you can do this process. So you take a strange quark out of your proton or nucleus, and if you do a charge current, you scatter that with a W, you make a charm quark, and that will decay to a charm jet. And you can measure that using the displaced vertex and look at the jet production. In fact, this is a project we did for the Yellow Book when they were studying different capabilities of the EIC. And here's the current estimate of the strange ratio, the strange compared to the UD. And you see here at x of 0.1 it's low. And then this is where fixed target is, this is where the collider is, and it's about sort of in the range of a half here, and it grows up there. And this is the relative variation, and I've done that with three strange distributions as a function of x. The gray band is the expected experimental uncertainty, and you see using 3 values of the strange ratio, that's well outside the experimental uncertainty. So, for example, this reconstructed x variable will allow you to discriminate between those two, and maybe we'll finally have an answer. So this is just one example of where the EIC can resolve some of these longstanding questions. And the challenge here is, much of this data, NUTAV was back in the 90s, and we don't have a lot of, updated data since then. The strange results from LHC I showed you, but it would be really nice to have this process so we can, really nail this down. Let me change gears and look at the gluon. And the gluon is interesting for a number of reasons. When I show you these PDF plots, I usually have to scale the gluon by a factor of 5 or 10 because the gluon grows up so quickly. At large X, it's small. It's dominated in large X by the upvalence and downvalence. But when you go to small x, it just grows enormously, and that's because the alpha S at low energy alpha S gets big. It's very easy to make gluon pairs, and you can just have a plethora of gluons. And so here's the cartoon. At low energy, I have a couple quarks and maybe a few gluons, and then as I go to small x, the gluons just sort of fill the entire proton or entire nuclei. And so you can get these collective effects, and you can look at all sorts of things like this, the quark gluon plasma. You can worry about recombination, saturation, things like that. And also dealing with nuclei instead of protons, there's just the geometric factor of 8 to the 1/3. When you take 208 nuclei and bunch them together, they're going to overlap. And so when I come through here, there's going to be effectively an additional 8 to the 1/3, which can bump things up. And that's an advantage, for example, that the EIC has over HERA. So there's a group working on this. In fact, this is based at Brookhaven. It's a SURGE collaboration. It's a topical nuclear theory group to discover and explore the gluon saturation region, quantum chromodynamics. It's based at Brookhaven, but involves people all across. And in fact, one of the things we're interested in is trying to improve on the gluon PDF, getting up to the LHC so we can look at some of these things. How can we get a handle on the gluon before we get to the EIC? Well, a couple things that CTEC has looked at is semi-inclusive hadron production. So the gluon is sensitive to that. Also, quark-only production. For example, the production of J-psi brings in the gluons. And so you could pull that in. Here's the actual data we use. We use a variety of data from Rick, from Phoenix and Star, and also from Elise at the LHC. And this is just a cartoon, but the gluon as a function of X. And basically, the gray is the original NCTEC. And then if you include these semi-inclusive hadronic data, you get an error where the orange band there. And so this really seems to help determine the gluon, particularly reduces the uncertainties of small x region. And again, this sort of gets us ready for the EIC, so we've got a good estimate of the gluon. So when we start asking questions about what it's doing at small x and comparing to the EIC data, we're ready to go. One other important thing we've done is to extend the X and Q kinematics. As I showed you at the beginning, we were really making very hard cuts in the data, and we were leaving half the data on the floor. We said, okay, we only understand QCD really well in this central region, and in these corners of the phase space, we're worried about it, so we'll just throw that data away. And this black cut is the traditional cut that we made in our global fits. This red cut is the extended cut, and we extend that in particular because these yellow points, orange points, are the JLab 6GeV data. And that's very powerful information at high X. But you can see if I use the conservative cuts, we leave all that out. So there's a lot of important information there, and we wanted to include that. But of course, if we include that, then we have to worry about various corrections that we talked about, deuteron corrections, higher twist, and target mass effects. But collaborating with the JLab folks, we actually were able to do this. And to just show you how much it improves things, here's the nuclear ratio. The black points are what we had in the original NCTEC fit. The red points are what's added by relaxing the cuts. So you see that's quite a bit. In particular, it really helps you in this intermediate and larger X region. What's still missing are these blue points. They still fall outside, and that gets to some very interesting kinematic regions. but maybe with some improved theoretical analysis, we can extend that a bit. But that's in progress. Okay. And it turns out one of the most important corrections to extend this turns out to be the deuteron correction. So the deuteron is naively just you take a proton and a neutron, put them together, and that's our simple model of a deuteron. But at large X, it turns out that that's not quite correct, and you have to treat that properly. And in fact, JLab has done extensive studies on this, and we use their corrections to do that. If we put these in, then we can get a good fit. And just for reference, here's the initial NC-Tech fit. It has a chi-square per degree of freedom of 0.81, so that looks pretty good. But if we just take that fit and extend it in the extended kinematic regions without doing anything special, the chi-square doubles to 1.7. But if we put in these additional corrections, we find out that the higher twist gives us about a 3% improvement. The deuteron gives us a 14% improvement, and the whole thing gives us a 16% improvement. So by adding these extra corrections, we can do an extended fit, and our chi-square per degree of freedom is 0.83, very comparable to NC-Tech. So the chi-squared is comparable, but the data set is more than double. And so with these extra theoretical ingredients, we can extend things out and include a much larger scope. And so that's one of the goals, is to be able to use these data to push the limits on what our experiments can do. I'm going to finish up with something completely different now, which touches on short-range corrections. And the idea is to connect up the nuclear and partonic properties. In what we've done so far, we've done a simple parameterization of the nuclear structure. So we assume the parton distributions are x to the something, 1 minus x to something else. We just add an A dependence and fit that. It's phenomenological, it works very well, but it doesn't really give us a way to say, why this nucleus is different than this nucleus, or this is special, this is a mere nucleus, this is isoscalar, what's going on. So we'd like to do that. And in what we do already, this is how we do it. We just add nuclear A dependence to the coefficients here, and we're sort of parameterizing things. We're doing a one-dimensional parameterization basically along the nuclear stability line. And of course, there's lots of structure here. Actually, that's what my dad did for a living at Brookhaven. But we're just sort of working along the nuclear stability line, keeping it simple. And so how would you handle this? So here's a cartoon of a lead nucleus. I guess protons are blue and neutrons are red in this convention. And how would you modify this from just saying it's a bag of protons and neutrons to something more complex like a coherent lead nucleus? And you think, well, I've got a proton over here and a neutron way over there. They're far apart. They're not going to interact much. You kind of expect that the interactions will happen with nearest neighbors. And that's what's suggested by this cartoon here. You've got all these nucleons, but only the nearest neighbors will interact. And so maybe, what's going on here to modify the nuclear structure is the short-range correlations, okay? And, if this were an E&M problem, how would you do it? Well, you have a charge distribution and say, okay, the first thing I do is I ask for the total charge. I ask for the monopole moment. And then I say, is it symmetric? Is there a dipole moment to it? And you do a dipole expansion. And if you want more and more detail, you expand out further and further. And so let's try that approach here with the nuclear structure. And so I'm going to try to model the nucleus as, to first order, it's going to be a free proton. And then I get the neutron by isospin. But then, sometimes the nuclei come near each other, and this will modify my distribution. So, here's my parton distribution for my free proton. And then, when two of them get close, they'll somehow modify this. And so it's sort of like a monopole and a dipole expansion. And then what I'm going to do is I'm going to guess that I can build up any nuclear combination by just making a linear combination of a monopole and a dipole. And I've got a coefficient here that tells me how much of this short range correlation inspired contribution. And then 1 minus it will be what's left over. Okay. And it's a very different parameterization from the standard in CTEC. And the question is, you can do this, but do these coefficients display any pattern? Maybe you can do this, but the coefficients will be crazy all over the map. It won't suggest anything. But let's see. First of all, can we even get a fit with this? Does it make any sort of sense? And sorry, I should back up and say this function is universal. So I'm in the end, I'm going to fit 19 different nuclei, but I'm going to use the free proton taken from, for example, for NCTEC, and then I will use this. I only have 2 functions, and then just by making linear combinations of that, I can get all the nuclei. So let's see how we do. So here's the traditional fit, about a chi-squared of 0.85. And there are 2 fits we do. One where we let the proton and neutron coefficients fluctuate independently, and then we link them in a way that I'll tell you in a moment. And what's first thing is surprising, not only do we get an okay fit, it's actually nominally better than the traditional fit. So this picture remarkably seems to behave not too badly. Okay, and you can see in detail, these are the chi-squared for, we have DIS, Australian, WZ, and JLab in particular, because that's what we're looking on. And it works particularly well for JLab at the higher X values. That'll be interesting to look at. So it fits pretty well, but do those coefficients have any sort of pattern? Is it completely random? Does it suggest something to you? And so what we did was we plotted what those coefficients are as a function of A. So this is the coefficient that mixes in basically the dipole moment. And you see for low A nuclei, you need about 10% of that dipole component, but at larger nuclei like lead, it's more like 25%. And so that's sort of interesting. We've just fit this to a linear curve, and more or less they seem to kind of line up along that. Some of these data points have large error bars because, for example, 131 we only have 4 data points, but where the data points are a little smaller, that seems to line up pretty good. The other thing you notice is that some of these are definitely off. Like let's see, this is I think lithium-6, and that seems to be off a bit. So what's going on there? Well, if you think about lithium-6, that's you can think of that as sort of a loosely bound lighter nuclei, and maybe that's suggesting that you should be interpreting more like a light nuclei down here. And so it's interesting because now you can talk about individual nuclei and say, why is this off? What's going on here? And you can start relating things to individual nuclei for the first time that the simple A parameterization doesn't allow you to do that. So that's kind of cute. But let me come back to this red and blue curve. So I said we fit the coefficients for the proton component and the neutron component separately. But what we found is, for example, let's look here at large A values for the, for example, for lead. What we found is that it seems that a higher fraction of the protons are participating in these short-range correlations compared to the neutron. And so, okay, that's odd. Maybe you expect the same fraction of protons would be interacting as the neutrons. But then you say, wait a minute, for very heavy nuclei, those are neutron rich. So for gold and lead, they typically have more neutrons than they have protons. So let's not look in terms of neutron, in terms of the fraction, but let's look in terms of the number. And so if I go and adjust these for the neutron excess, okay, now I go from this dotted curve to this blue curve, and you see those align much more closely. And so, this is interesting because it suggests that not the fraction, but the number of neutrons and the number of protons participating in short-range correlations seem to be the same. Let me just give you some details in terms of one example. Let me take gold, which is 197.79, and we estimate that basically 25% of the protons seem to be involved in these short-range correlations, whereas only 17% of the neutrons are. But you take into account the number of neutrons and protons, you multiply that out, and this is just for illustration, in this simple calculating, it says basically 20 of the protons and 20 of the neutrons seem to be participating. And so it's very curious that those come out to be the same number, because separately there's a hypothesis that in these SRC pairs, the number of protons and neutrons are equal. That is, there's a suggestion that these short-range correlations are typically proton-neutron pairs instead of proton-proton and proton-neutron. And what's interesting about this, had this come out different, we could have disproved that hypothesis. If these came out different and say, no, that doesn't work, you're going to have more than one or the other. But this doesn't prove it, but it is consistent with it. And so that was a curious, sort of the second curious observation about this. And so, this is relatively new work. We're going to sort of pursue this in a few directions. But from our point of view, what's interesting is the simple nearest neighbor SRC inspired form. And this is purely a model. It's inspired by the SRC, but it doesn't depend on any of the details, the underlying theory of that. It seems to give a remarkably good fit, even better than the traditional fit. And that's fully taking into account the degrees of freedom. Comparable or better than the traditional approach. And the coefficients seem to scale roughly with log A. And then separately, when we separately fit the proton and neutron coefficients, it seems to be consistent, suggesting that the equal number of protons and neutrons participate, which is consistent with this idea that these SRC pairs are proton-neutron. And it allows us to go here and relate to individual nuclear quantities. Once we have better uncertainties on this, we can say, hey, this lithium seems to be a bound state of 2 lighter nuclei, and you can go and look at other ones. And again, maybe address the fact of, some are, as I said, some are isoscalar, they're like at mere nuclei, some are far from the nuclear stability line, things like that. So anyway, that's sort of something a little bit different. So there's, as I say, a bright future ahead. And this is from the website, the EIC, a machine that will act the secrets of the strongest force in nature. And let me just give credit to the various people that worked in these. I worked in pieces of these, but it's a large group of pieces that put that all together. And so that's great. We, a decade ago, we put out NCTEC 15, and, you have many PDFs that you can choose from. But instead of having many you can choose from, you really want one. And to put that in perspective, how far we've come with this. So this was what we had a decade ago in NCTEC 15. We used 3 data sets, deep inelastic scattering, Drell-Yan, and some limited semi-inclusive hadronic production. And we were sort of confined in this corner of the phase space. The solid points are the ones that we included. The gray ones are the ones that are cut out by our very strong cuts. And at the end of the day, we had about 700 data points. And this is what's in progress. I should have updated that. We're going to be calling that NCTEC 25. But we've gone from 3 to now 8 processes. We've added DIS, dimuon, WZ production, onium, open heavy flavor production, and we've gone from 700 points, about 3,500 points over a much larger part of the phase space, and also included increased kinematic reach. So that will set the stage for what comes next, and I should give proper credit to these folks, Thomas, Katrin, Jan, and Oleg, who are leading this effort, and this will be coming out shortly. But you can sort of see the pattern. We put out NCTEC 15. This comes out about 10 years later. You can expect maybe the next consolidated update in the mid-30s. But the bottom line is this will be what we use for the high Lumi LHC and then the initial data sets at the EIC. So this will be a useful reference set. And of course, there are other ones. There's NNPDF has done some, EPS have done some, but you're getting the CTEC perspective. So let me just conclude, coming back to this statement. The most exciting phrase here in science is not eureka, but that's funny. You see funny things, and I've shown you a few things like the strange quark doesn't seem to line up. These SRCs are suggestive, but we don't quite have enough information. And what's going on with the gluon? We've seen quark-gluon plasma, but there are lots of open questions there. And so we have lots of places that we can say, gee, that's funny. But I think the combination of the high LUMI LHC, which will turn on shortly, and then the EIC is going to give us a big handle on that. But I'll finish with this quote from Louis Pasteur: "Chance favors a prepared mind." So we can't just wait around for the data to make us smarter, but we have to prep for this. And there's a lot of work going on behind the scenes using the current data as we get ready for this. And I've given you, it's just sort of snapshots of what's going on. But that's what's happening now, and what we can expect going forward. So I will finish there, and actually let me just come back to this, because I think this one really, expanding these corners are going to be a challenge. If we really understand QCD, we'll be able to go into these corners and nail that down. So anyway, I'll finish there, and thanks for your attention.
Yep.
So for the deuteron corrections, are you using complete finding approximation?
So it's inspired by that, but essentially Alberto Accardi helped us with that. He gave us some fixed tables that we used to adjust that X-dependent, and basically was that ratio I showed you there. And those the target mass corrections help a little bit, but the deuteron corrections are particularly helpful. And also many of the nuclear data are put in the form of a ratio. And very often the denominator is the deuteron. So it influences lots and lots of things. But I showed you if I just take NCTEC 15, open it up and drop it in, the chi-square blows up. And the deuteron corrections were a big part in fitting that. But all the pieces together seem to go in there. So that's what we're using. But they're absolutely essential for that data set, particularly the high X.
Have you explored the decimal correction for helium-3?
That's
the machinery in place.
Yeah, that's interesting, because there's data on helium-3 and now there's data on tritium. And in our parameterization, they have A of 3, we're going to treat them the same, whereas they're clearly not. So those light nuclei, we're working with a broad brush saying, okay, it just goes as A. That really kind of breaks down in the low A region, and that's where we need some thought and some extra input. So we right now we sort of sidestep that. If you look at our main data sets, we have a lot of lead from LHC and Chorus, gold from Rick, iron is NUTEV, carbon is JLab, but we've sidestepped the low nuclei, and in particular, that's also some of the lattice stuff is looking at low A. They can't go high up in A, but if they can do A1, 2, 3, that'll be a big step. Right now that's probably a weak point, and we need some careful thought and more input there. So yeah, that's definitely an open question.
Can you say more back on slide 38 of the SRC error function? Can you say maybe more?
38.
Yeah, 38.
Oh, 38. Here.
Could you maybe say about how you actually go about getting this SRC function?
Okay, yeah. So when we do this, we freeze the proton. We assume the proton we just take a proton off the shelf. And then what we basically fit a functional form, and we'll use the same framework as we did before. So x to the something, 1 minus x to the something, we'll do that. And then we do fit the coefficients. Okay, so we have about 19 parameters in here. And then we have, for the coefficients, if we're doing 19 nuclei, we'll have 19 pairs of coefficients. If they're isoscalar, we assume the proton and neutron are the same. If they're not isoscalar, in one of the fits, we allow them to separate. So that means we'll have a little bit more than the nominal number of degrees of freedom. But when I calculated the chi-squared, I calculated that properly. That was per degrees of freedom, not data points. And so this is frozen, and then we let this wiggle a bit to get the best fit, both the form of this and the C values. But when we're done, basically this is frozen, and then these C values determine what my PDF is at Q0. That gives me Q0, and then we just evolve all 19 nuclear PDFs, and that does it for me. So it's a completely different way of doing the parameterization. And also, this is A-dependent universal. So this gives you a very neat connection between all A, because I'm using the same underlying piece for that. So you can make some interesting observations about the structure there. And then again, what's particularly interesting is then now you can go and, because in some sense you're doing experiments not sort of tying the A together in the same way, but you're allowing this to vary nucleon by nucleon. And so when you see an outlier, you say, what's going on there? Why is that nuclei behaving different? If this comes out being high, what's going on there? And you can start addressing individual nuclei, which is something you can't do with the previous broad brush A parameterization. So we did one study on this. There's lots more directions we can do, but the number of sort of things that the number of times said, "Gee, that's funny," was quite a few, and so this merits more investigation.
For not an expert such as I am, if you go back to slide 38, actually.
38.
So the EMT effect itself has a funny shape, isn't it? And there are all these words like Fermi motion, shadowing, anti-shadowing. Can you say a few words about what's physics? What shadows what?
Yeah. So one element is because we check where I do the parameterization. Because we do the parameterization, we just do an X of something, 1 minus X of something. This is not put in at all. That simply comes out of the fit, and then the combination is, it seems like when you go to very low extra shadowing, and you expect maybe the nucleons are sort of overlapping a little bit at small x, and that's giving you a decrease. And then this anti-shadowing, it goes above 1. And there's some hypothesis about the mechanisms. And actually that's not my, I'll defer to the nuclear theorists about that. I'm giving this more of a phenomenological region. And then this is called the EMC region, where it sort of dips down about 10%. And this fermion region is sort of interesting because there, in a proton, you can't have any of the partons have more momentum than the proton itself. So you're strictly limited to X of 1. But if you start putting multiple nuclei together, then they can kind of trade a little bit, and one can give the other a boost and it can push it past 1. And so, that can give rise to this kind of phenomenon where for iron, you see that, the number of very high partons can be greater than that is what it is in proton, because you can have this trading across. And that's an A dependence. We actually have there's a more complicated convolutional model for that, but we tried a rather simple smearing, A-dependent smearing function that actually does pretty well. And so that might be a region. As I showed you, even though we pick up a lot of the data in this region by expanding the kinematic cuts, this region is still excluded, but we might have some models that can take that into account. But when you go there, you risk, you're in the resonance region, so you've got got to deal with that, although some of the folks at JLab have these, proximate, you sort of smear across a resonance. And, but you can do a smearing where you say, gee, I'm going to take A and bump it out some A-dependent part. And then actually you can start to fit things like that.
Great. Questions? We're ready for the coffee, so let's.
It's coffee time.